Welcome back to another HVAC-Engineering-Techie training video. Today our training video is on HVAC pneumatic control systems. Now, we don't use a lot of pneumatics like we used to, but we still use them for overlays to push stuff around like valves and dampers. And we use them for you got explosion-proof atmospheres. It works well for there too. So we'll be talking about pneumatics in general terms to give you an idea what they are. We won't be going really deep into pneumatic logic. It gets to be very complicated, and there's no reason to because we don't use that anymore at all. So remember, this is the channel that talks all things HVAC, engineering, design, construction, equipment, systems, test and balance, controls, efficiency, and performance. So I'd like to ask you a favor before we start. Would you please become a subscribing member? Boy, I'd really appreciate it. It costs you nothing. It's absolutely free. You just have to click that subscribe button. If you like the videos, give me a thumbs up. And the reason for that is that Google doesn't use that data to bug you. I don't bug you, so it's no one's ever going to contact you from the data you put in there. But it just makes you a subscriber, and that's how Google evaluates my videos, by how many likes I get and how many subscribers I get. So that would really be helpful. And if you're already a subscriber, boy, I really appreciate it. Thank you very, very much. All right, let's get started. Let's talk about pneumatic controls. Before we get started, we'll just kind of look at our training videos that are available for our control division. Well, you know, you've seen this before, but we'll try to get through this quickly. C1 is HVAC control system basics. C2 is DDC controllers and network devices. C3 is DDC control architecture. C4 is DDC control components and devices. C5 is DDC control installation and wiring. C6 is water-cooled central plant system sequences. C7 is hot water control central plant control system sequences. C8 is chill water central plant control system sequences. C9 is constant volume air handler control system sequences. C10 is VAV air handler control system sequences. C11 is outside air handling unit control system sequences. And all these sequences sessions are basically a deep dive into the sequences and reset sequences. And we're using the guideline, ASHRAE Guideline 36 examples of how to do resets, which have been a problem in our industry. C12, tuning DDC control loops. C13, how to select and size control valves. C14, how to select and size control dampers. And C15, which is this video on HVAC pneumatic controls. All right, pneumatic controls. The history, I thought that when I first got into controls, I thought the history of controls was interesting. On and off electric controls started around 1835. When electricity was just first getting off the ground. So we started using to start-stop devices, fans, the motors, and that was on off in 1835. And the pneumatic HVAC controls came around about 1900, and it was created to give proportional controls. Because electric controls on and off is easy, but proportional is not possible. It doesn't do proportional. And even today, our DDC controls don't actually do proportional. We have all kinds of ways of trying to emulate what modulation is, but it's not true proportional modulation. But pneumatic is. Pneumatic's naturally proportional. And where I first learned this when I became a Barber Coleman rep in controls, they had their very first humidistat, which was a pneumatic control device, and it was designed to control the humidity in mills that were making cloth. And that was where they got started in pneumatics, and I thought that was interesting. Digital controls came around 1960. The control world we live in has not been around that long, not really. Now, for some of you younger folks, it may seem like a long time, but for me, this was yesterday. And I remember the first systems that came out, they were not like you're thinking today. They weren't networked. There's no such thing as network, but they were digital, and they just used different devices to communicate, and we thought they were really slick. Advantages of pneumatic controls. Naturally or proportional. They come out of the box natural proportional, and you have to make them be not proportional. High accumulate actuation power, very fast action. So a pneumatic can have a lot of power. You know, you can run 85, 125 PSI, and you can move some big valves and big dampers because you have so much force. They are very fast acting. Now, if you're trying to remember that most electric actuators are all motorized, and they take time. Like 30 seconds is a fast actuator. 15 seconds is a really fast actuator. But that's not very fast. If you're trying to catch a pressure wave, which is moving in a pipe at 600 miles an hour, You're not going to do it with electric. You're just not. You're going to either have to have hydraulic or you're going to have pneumatic. Now, where this became real to me is when I was doing chill water storage. I had a 1.5 million gallon tank or 500,000 gallon tank on another job. And what happens, these tanks are open to the atmosphere. So your chill water system's a closed chill water system, but when you dump the water in the tank, it's now open. So if you don't have a way of controlling pressure of the water entering the tank, it will drain the water from the system into the tank. And then when you have to fill up the pipe again when you start over. What that does, it introduces oxygen and corrosion into the system. So we put valves on that entering water to hold back pressure so that water could not drain into the tank. It would, as soon as the system would stop, it would stop. And you can't use electric control valve because it would take 30, 60 seconds to close and the water would drain out. Well, that's 60 seconds. You can use a clay valve, which is a hydraulic valve, and it will do it. Or else you can just put a pneumatic valve with a direct pneumatic pressure controller and it will control it fine. So that's because it's very, very fast. Naturally explosion proof. Air doesn't explode. There's no electrics. Make sure you don't have an electric device in there. So you can have a sensor in there that senses fine and no electricity needed. And they have a long lifetime, the system does. However, they have disadvantages. And the disadvantages, they require clean, dry air. If you pump water into them, yeah, I'm sorry, sir, you just ruined your system. Now, in the old days, back when Powers was making pneumatic controls, by old days, I mean 1965, 66, you could put water in them and they just drain out and you could keep on going. But modern pneumatic controls, by modern I mean from 1975 on, if you put water in them, you bend the burden tubes and it's now totally out of calibration. And sometimes it's so bad you can't calibrate it after they have to replace the device. I remember a sad day when I had a hotel call me and say that they have a problem with our thermostats. I said, what's the problem? He says they won't calibrate. So what do you mean? Well, you try to calibrate them and they just won't calibrate. I said, when did you put water? When did the water event happen? And they said, oh, well, that was 2 weeks ago. We had a problem with air compressors. We pumped the system full of water, but we drained it, and then we put nitrogen in it to dry it all out. And I said, well, I hate to tell you this, but you've just damaged and ruined every thermostat, all 385 of them. It's a hotel, and they said, what do you mean? I said, you got to buy new thermostats. These cannot be fixed because you damaged them with water. You cannot have water in the system. That was a bad day for that operator, but it's the truth to say. Clean, dry air is very, very important, and we do all kinds of things to make sure this is clean, dry air. High maintenance cost requires calibration. The pneumatic devices need to be calibrated once or at least twice a year. And in some critical, they're done monthly. So this maintenance cost is high for the calibration. Difficult to create control logic. You can do it. I've seen guys do it, but man, is it complicated. So it's much easier to use pneumatics to push things around and let DDC do the thinking. That's what I've always said. No more expensive. Now it's more expensive than digital controls used to be. You could do something fairly inexpensive, but nowadays, a controller used to be $85. Now a controller might be $500. I've seen $800 reset controllers, which is crazy. So unfortunately, the pneumatics, is because they don't use as many as they used to, I guess, are now more expensive than digital. Here's the pneumatic control system basic layout, and this is the key, trying to prevent any moisture from getting in. So what's happening? These compressors on this compressor tank will pull in outside air and will pressurize it up to probably 125 psi or so. And in doing so, they heat the air way up. And when the hot air gets in here, as it cools, it will condense water, and so it will start building up water in the tank. And this happens even with my home compressor. I have to blow the thing out every once in a while because it'll fill up with water. I'm just running tools, so it doesn't really bother me very much, but I do that. So to solve that problem, we put an auto tank drain. And this tank drain, there's two types. There's one, there's just a solenoid valve, and a timer opens it up 10 minutes a day or 5 minutes a day or 2 minutes a day, to be able to blow out what's in there, and it does it every single day. Or we have one that's pressure actuated, and it will do the same thing. It's kind of like a timer motor, but it's pressure actuated to blow it down. Now, these are very important. You can do it manually, but don't forget. If you forget, you could damage your system. So then the air comes out of the tank and goes through a pre-filter and an oil filter to get the oil out of the system. Now, if you're using an air system that's doing tools, you want oil in it, but for this system, it's got to be oil-free air. They can use a standard compressor, or you can use an oil-free compressor like the vane guide compressor, and it will give you that deal. And then we have an air dryer, and these are normally refrigerated air dryers, so that they can drop all the moisture out of this air. You know, this, even if we have a dry tank and this humidity is high, it could push some of that humid air down the stream. So we're going to take that out with getting very, very cold suction gas, 45 degrees or so, in this air dryer to drop out the moisture. Now, they do make chill water dehumidifiers, which do work. But unfortunately, if you reset your chill water up, because to get energy efficiency during the winter, now you've just defeated your air dryer. So refrigerated air dryer is the gold standard. And then you have a post filter just in case anything gets through there. And then you go out and you normally have then a pressure reducing station, and your distribution, high pressure distribution, is 65 to 85 psi. This may all be 125 psi. And then you have branch mains that will go down to 30 psi. And then you go to the controller, and then the controller is going to run between 18 and 20 psi to the valves or dampers. So that's the way air works. And the important thing is clean, dry air. Compressors must be sized for both the maximum air demand and compressor runtime of no more than 33%. Compressors need to be 600 RPM redundant units with refrigerated air dryer filters, automatic tank drain, and PRVs to supply 30 psi to the main. This compressor, you know, you're not going to go down to Home Depot and buy a compressor for a control system. And it ain't going to work, because these are the single point of failure of the entire system. So you cannot have this fail. So we use redundant compressors, which are set for 33% runtime and are redundant. So this one can run, and then this run, and normally have them on alternators, so they run back and forth. And then we have a certain size tank, and we're going to go through the calculations on how you size these. But this is all very, very important. And manufacturers make compressors just for control air. So they have all the requirements you need already on them. Here's a typical one. Remember, I'm just showing you a picture for training. Not saying any brand. There's all kinds of different brands. This one has got two different compressors, slow RPM compressors, has a panel that alternates, does all the control of those. And then it has automatic feed on it. This is the pressure controller. So it's got air dryers. This is a refrigerated air dryer. This one might look like. This is a low pressure, in other words, a 18-pound pneumatic actuator. And you can see it's got a diaphragm up here. And the pressure comes in and pushes this down against the spring. The spring pushes it back up. High pressure valves. This has a double acting actuator in there. So this controller puts high pressure in one way and then puts high pressure in the other way and relieves the air to do that. And these would be valves or dampers, either one. So high pressure. This is the one that we use a lot nowadays. And the reason is because you can get a 125-pound PSI or an 85 PSI actuator for a large valve, say a 14 or an 18 or 20-inch valve, a lot cheaper. You can get an electrical one. And it's going to be dependable. It's going to be last a long time, and it's going to work very, very fast. So that's why these are popular. And this is a low-pressure damper actuator. This high-pressure damper actuator is just a beefier cylinder, but it pushes both ways. That's what this device is doing. We have room temperature sensors. Now, the difference between pneumatic and electronic is that you buy sensors and devices either normally open or normally closed, because that's reverse acting or direct acting. So you need to know, and we'll talk about this in a little bit, what you're doing. Room humidity sensors, normally open, normally closed. Duct temperature sensors, normally open, normally closed. Duct humidity sensors, normally open, normally closed. Duct pressure sensors, hydronic pressure sensors, receiver controllers. Now, receiver controllers are unique in that every manufacturer makes one. They look totally different. I mean, they look drastically different. And they all calibrate differently, so you got to have the manufacturer's instruction if you're going to try to calibrate one. Air relays. These relays will do different things, and we'll go over that. PE switches, which are pneumatic electric switches. So this is how to get a pneumatic signal to provide an electric signal on and off. EP switches are electric pneumatic, which is a solenoid valve. VAV Velocitrol, this is actually a reset controller, but just for a VAV box. You can tell this doesn't look totally different, right? And here's the basis of how everything actually works. This is, and all pneumatics work the same, and all manufacturers work the same. So you have a supply air, say around 20 psi, you got to be at least 20 psi or above, and that airstream comes in through a restrictor. This restrictor only allows so much airflow, and then it goes down to, say, a thermostat. And the thermostat has a bimetal spring on it that actually allows this air to escape. So if it needs to make a change, if this pressure is too high and it needs to lower it, like he wants to lower that, it will open that and bleed a little bit of air out of here. So this pressure goes down, so that spring returns this actuator. And what's happening here is this device here is sized to release more air than this restrictor. So if this has 20 pounds entering and this is closed, this will be 20 pounds on the valve. When this opens and it starts relieving twice as much air, this may go down to 10 pounds, even though there's still air coming in and the air is releasing here, so it's 10 pounds. When this is wide open, it's big enough to be able to have this have almost zero pressure in this device. And this is how all pneumatics work. So the pneumatic systems use air. They utilize air, but valves and dampers, actuators do not use air. What uses air is a thermostat or the sensing device. So when you're sizing a system, you have to add up the air usage of all these devices to be able to make sure you got the pipe sizes correct and the compressor size correct. But all pneumatic systems work this way. The valve actuator pushes down the diaphragm against the spring. The air pressure is changed by the thermostat relieving more air than the restrictor can flow, thus reducing the air pressure. So sometimes you have to replace a restrictor with a smaller one if the one's too big. Or you might have to have another device that relieves air quicker. You might have another device that opens its main to atmosphere so that this is guaranteed to be zero pressure. This is a room temperature control diagram. So this is the diagram. This has to be reverse acting because it's going to the left. In other words, as the temperature rises, the pressure decreases. So it's a reverse acting. And so this is the throttling range for a hot water valve. So we have a hot water valve here. So we have a hot water valve normally closed 8 to 13 pounds. And we have a chill water valve that's normally open 3 to 8 pounds. That's this normally open, normally closed stuff. And we have these spring ranges. So each valve has a different spring range. And you'll see they both have 8 pounds. So that means right here, this one's closed. So if we're 70 degrees, the hot water valve is fully open. And as the temperature gets higher, it begins to close until it reaches this point, which is a set point, it closes. And then if we're here, and this chill water valve it's getting hot, so it starts to open. So the chill water valve is open here. So the throttling range for the hot water valve is 70 to 75. The throttling range for the chill water valve is 75 to 80. And the throttling range for the system is 70 to 80. The span of the sensor is 55 to 85. In other words, the room sensor for this, we'll get to this in a second. So throttling range, the proportional range a sensor must have to operate an actuator from full closed to full open. So this is the throttling range of the system. So at this point, the system is in heating full, and this one is in cooling full. And this is the span of the system. So the proportional band is the percent the throttling range is to the span of the sensor. So the proportional band is the throttling range divided by the span, which equals 100 times 100, which in this case, so if you have a room shown in the control diagram at right, would have a proportional band for the system. It would be 80 minus 70 divided by 85 minus 55 times 100 would equals 33%. It's the proportional band. Now, you only need to know that if you're trying to calibrate a reset controller. All right, so here's one that's normally acting. You see that it's going in the same direction, and that's the definition of normally acting, reverse acting. So here's this system. So it has a thermostat, 20-pound air coming in. It has one line that goes out and connects to both valves. So as this pressure changes, it's moving both valves. So if the system's at 70 degrees, it means the hot water valve is open. And it's a normally open 3 to 8 pound valve, and the chilled water valve is a 3 to 8 normally closed. So at 70 degrees, this is open, and at 75, it's closed. And at 75, the chilled water valve is closed, and at 80 degrees, it's open. So this is a direct acting. Increase in temperature equals an increase in pressure. It's a force pressure diagram. Reverse acting thermostat, same thing like we just talked about. So it's in the opposite direction. Increase in temperature equals a decrease in pressure. Thermostat calibration. Okay, so when I used to talk to control technicians, I asked them, well, how do you calculate the thermostat? They said, we just take a gauge and we calibrate it at 8 psi. And you go, okay, that's not actually the right answer. And the reason it's not the right answer is here's the 8 pound came from. You have a 3 to 13 actuator. So you subtract the 3 from the 13, you get 10 pounds. So this actuator has a range of 10 pounds. Take the 10 pounds and divide it by 2, which is half where you want to be. That equals 5. So 5 plus the starting pressure of 3 equals 8. That's where it comes about. Well, what if you have a 0 to 10 psi actuator? No longer 8 psi. Or if you have a 5 to 18 pounds. And this is all about spring ranges. So the 8 psi is correct for a 313. It's not correct for a different spring range. So we need to make sure that the technicians understand how this actually works and not just use 8 pounds. Receiver controller calibration requires all sensor spans, throttling ranges, and percent authorities and then follow the manufacturer's instructions. Because they're all different. I mean, they're drastically different, not similar at all. Two-way globe valves. Verify the shutoff pressure that can lift the valve off the seat. Remember that if the fluid pressure is high, it can overcome the spring. It can actually lift the valve. Size for slightly higher pressure dropped in the load, just like any other valve. Verify flow direction. Specify normally open or normally closed. Three-way mixing globe valves. Mixes 2 streams into 1. Size for slightly higher pressure that dropped in the load. Verifies pipe to the control layout, because you can pipe these 2 different ways. So that's important. Verify normally open or normally closed, stem up or stem down. This is a new catch. Because they make actuators with springs on top and they make actuators with springs on the bottom. So you can be normally open or normally closed on the valve. It depends on which way the spring is going. So that's what you have to make sure on a pneumatic. This is different. On DDC, you don't have to worry about that, but on pneumatic, you do. Here's a large butterfly valve high pressure actuation. So one of the applications nowadays for pneumatic controls is if you have a large central plant with large pipe sizes, say 24-inch pipe or 18-inch pipe or even 12-inch pipe, the valves for electric get really expensive in those sizes, but they're not so expensive in pneumatic. So what you buy is you buy high pressure actuation for all your valves in the central plant. You have a central plant air system that runs pressure to those valves, and you run electrical to those valves, and it controls the valve. And here's how it works. So we have a double-sided active cylinder, air cylinder. So you put pressure to one side, it moves, it opens it, put pressure to the other side, it closes it. And this is the device, this 4-way solenoid valve. So you have the electric control signal come in and say, I want it open or closed. And what it does, it connects these 2 pipes, this one to this one, and then this one to the bleed air. So what happens when you put it in one position, one side is open to bleed air, and one side is open to pressure. When you put it the other way, the other one is open to pressure, and the other one is open to bleed air. Because realize this won't work unless you bleed the air off the back side. So the actuator doesn't use air, but this device does use air as it allows you to open and close the valve. As this one opens and closes the valve. Pneumatic valves are less expensive than electric control valves. Common to see central plant valves all controlled by pneumatic with a DDC system overlay. System design. Okay, this is a little interesting here. So air tube sizing. This is a skim. This is standard cubic inch measurements in bleed air by device type. Now, some manufacturers use air units, which is 16 skims for an air unit, but I prefer just to use skims. There's no reason to have a different in there. And this is a typical list of control manufacturers' products and their leakage rate. What air do they use? Here's it at 15 psi, here's it at 20 psi, depending on what psi you're supplying that device. So pneumatic relays, ratio relays, selection relay, electronic transducer, DP controller, differential pressure control, wall thermostat, aspirating thermostat. So a wall thermostat at 15 psi will use 16 skims, which is per minute, or if it's a 20 psi, it still uses 16 skims. Now, an aspirating thermostat, what that is a thermostat that actually sucks in air from the space and then measures it across and puts that way. So it's actually sucking in air, and it's actually using that. It's not just an element on the wall, it's actually breathing in air. And those use 48 to 64 skims, so they use a lot of air. And these are designed a lot of times for explosion-proof applications, or they might be in prisons or somewhere where it's secure, where you don't want it exposed. Switching relay thermostat, aspirating switch relay thermostat, remote bulb thermostat, remote set point adjuster, humidity transmitter, differential pressure transmitter, receiver controller, velocitrons. So all of these devices use air, and this is what you use to calculate air. So total air, all air-using devices, flow rates per branch main. Flow rates will be in skims or bleed units. One bleed unit equals 16 skim. One skim equals 1 CFM, standard CFM equals 1,728 skims. So skims, pretty small measurement. But it's really important that you figure out everything that uses air. When I was a control contractor, I did a university job, and we had, 250 boxes on this job or something. It was a dual duct box job. And I forgot that velocitrons actually use air. I had all the thermostats and everything, but I left off all the velocitrons. So basically, I was half size of all my tubing requirements. So that was kind of a shock that I had to go in and fix that. And what I did is I just upped the main pressure and had to put a pipe in a couple of double mains just to get it to there. But it worked, but it's embarrassing not to include all of the actual air-using devices. Normal line pressure, high pressure distribution mains, 85 to 65 psi. 20 psi loss is okay for that. Branch mains, 30 psi. You want to use a 1 psi loss. Device control at 20 psi, you want to use a 0.2 psi loss, because you don't want more than 1.2 psi loss from the branch down to the device. This main at high pressure, you can run clear to 125. You can use a 20 psi loss, because you can run 125 psi and still have 80 psi out. This is pretty high. I don't normally use that, but you can use that high. Using the table or charts to size each main for length for a maximum system pressure drop of 1.2 psi, using 1 psi drop for the main and 2 psi for the branch. So here's a copper tube skim flow rate at 75 psi at a 20 psi drop. So here's the length of the total length of the footage run, and this is the skims that it will do. And this is a copper tube skim, again, at 30 psi at a 1 psi drop. So a main flow is, here's an example. Main flow is 11,482 skims at 80 psi with a run of 765 beat. What size of tube will be used at a 20 psi maximum drop? So from the copper table, select the 800-foot row. Okay, so we're at 800 feet. It's longer than the 765 psi. And go across till we get 16,000 skims. So we're going to go across. That's too small. Oh, that's way too large. So ½ inch is the right choice. A main flow is 1,482 skims at a 30 psi with a run of 385 feet. What size tube would be used at a 1 psi pressure drop? And the same thing with a copper tube at 400 feet. You go across until you get more than that 1,480 feet, which would be ½ inch again. Okay, now air tubing, plastic tubing, has different tables because it doesn't have the same smoothness as copper tubing. So here's the 1 psi drop table at 30 psi. Here's a 0.2 psi drop at 20 psi. So a sub-main flow is 982 skims at 30 psi with a run of 250 feet. What size tube would be with a 1 point drop? So again, you do the same thing. Go to the 300 feet, which is longer than 250 feet, and go across until you get greater than the 2080, then you get greater than the 982. So from 3/8 to half, it's quite a spread, but it's going to take a half again. A branch flow main at 322 skims at 20 psi with a run of 185 feet, what size tubing should be? Same thing. So we go take up the 200 feet, go across until we reach more than 200 feet, which is 3/8. So this could be 3/8 main. And that's why you size the tubing. Now, compressor sizing is more complicated, but here's how we do it. Using the total skim or CFM for all connected air using devices, size the air compressor. Total all air using devices, flow rates per branch main. Flow rates will be in skim or bleed units. One bleed unit is skim. One skim equals 1728 CFM. Normal line pressures. High pressure distribution mains 85 to 65 psi. Branch mains 30 psi. Device controls 20 psi. Using flow tables or size charts, each main for length for maximum system pressure drop 1.2 use 1 psi, just like we did before. Control compressors are sized at either 33 or 50%, but it really should be 33%. 50% you can, but we normally don't. Normally 33 is the correct way. Control compressors need to be low, 600 RPM, redundant units. It could be 608, 610, 540, you don't know, but around that range. For standby service, compressor tank must be sized for the number of compressor starts in 1 hour, normally a maximum of 10 starts an hour. Refrigerator, air dryer, and filters, pressure reducers are all sized based upon maximum airflow of the system. And this is the typical compressor ratings of CFM. Now, this is a generalization, so you would need to actually see a manufacturer's submittal to figure out which one you're going to use. But if you're CFM at 33%, and this is horsepower, so like say a 5 horsepower is 7.8 CFM, and then tank size is normally about 80 gallons for that one, and free air is at 100 psi is 20 CFM. But this is what we normally, this is size, so you get down to small compressors here. And we don't normally have compressors over 15 horsepower, to tell you the truth. This is a whole bunch of air for a control system, and you'll see as we go through and size this. So first, total the skims, then find that is, turn it into CFM, size compressor for 33% runtime, derate compressor for altitude. That's the next thing you do, because this is air, so if you're in a high altitude, you got to derate that compressor, because it won't. At high altitude, the compressor will not pump as much air as it will at low altitude. Select the compressor, calculate the actual runtime, calculate minimum tank volume, select filter and dryers, total CFM and the flow rate. So here's an example. A pneumatic control system has a total of 2,483 skims. What size of compressor will be required with a 20 psi differential? That's a start-stop differential. Or 33% runtime, and a compressor is located at 3,000 foot altitude. So it's not at sea level. So for step 2, CFM equals skim divided by 1728. So we have 2483 divided by that. We got a 1.43 CFM. CFM, we're going to step 3, size of compressor for 33%. So it's 1.43 divided by 33, which means we have to have a compressor to do 4.35 CFM to be able to do 33% run. Step 4, alternate rate is about 3% per 1,000 feet. So we have 3 of those, so we're at a 9% increase. So the CFM of a compressor 4.35 times 1.09 equals a compressor at 4.74. So we need to be able to do 4.74 CFM at pressure. Step 5, either 3 horsepower or 465 horsepower at 780. So depending on what we're doing there, we'll go back and look at that in a minute. Step 6, runtime system. Let's go back and look at that quite quick. Let's get that table. I didn't put that table up here so you could see that. Sorry about that. We'll get there. Okay, here's the table. So we're looking at 4.5 CFM at 3, so 4.66, which would be 3 horsepower, 60, or a 7.8 at 5 horsepower at 80 gallons. So either one of those would work. We're going to get back down to our example. Okay, so either a 3 horsepower at 4.66 or a 5 horsepower at 780. It depends on what you want to have some extra standby. Runtime, system CFM divided by compressor CFM. So runtime is a 1.439. That's what we need to have. Divided by 4.35. It's a runtime of 0.3303. It's slightly over 33%. So off a runtime, 60 starts per hour at one time minus runtime. Maximum starts per hour 10, so 110 constant factor. Off time would be 60 times 100 minus 33 equals 4.02 minutes. Minimum tank size would be 110, which is this constant factor, times 1.439 times 4402 divided by 20. And it means the tank size would need to be 31.77, but the supplier will supply a 60-gallon with a 3 horsepower system. I can't remember what this 110 is made of, but if I remember right, it's made up of a circular cylinder, and it allows you to calculate the CFM to gallons. It doesn't. I tried to reproduce that, but I couldn't figure it out, so not sure what it is. But that's what's in the books. Off time is 60, but divided by 30.1, so it's this tank size equals 4.02, 7.59 minutes. Starts per hour, 60 times 1 minus 0.3303, which is the percent of runtime, divided by 7.59 equals 5.29. Final compressor is 3 horsepower duplex, 60-gallon tank, 20-pound differential, 5.29 starts per hour. So we're considerably under the 10 starts an hour, so that's a fine selection. We didn't need to go to the bigger unit. Now, you might want to cut that out to follow that if that's a little fast going through all that, but I don't think we need to labor it. But that's how you size a compressor. Now, let's talk about ranging. This is some of the fine-tuning of that. So you have 2 valves, and this valve is a normally closed 8 to 13, and this hot water valve normally open 3 to 7. So what you want, but you want to have a dead band. So you want that the hot water valve be a 3 to 7, and then you want the other valve to be a 9 to 13, because you want to put a dead band of 2 degrees in there. To do that, you have to have a positive positioner relay, which will allow you to change the signal. So what happens is when you turn this room thermostat comes on, and it starts modulating that, this pressure goes up here and resets this reset relay, which has main pressure on it, and it will actually reset that range by 2 degrees. Now we're set to 9 to 13. Even though it's an 1813 valve, we are not going to let it do anything until it gets to 9 pounds. So it will change that operation. And that's how you adjust these linkages where you want to go. You also have relays in there that will allow this to have more air, because you see you got air coming right into this device. So this will make this actuator quicker, because it's actually giving more air than this thermostat. The thermostat's a pretty limiting device, but you can put a relay up here that has a much larger orifice in it, and it'll move this up and down much quicker. So that's the one way to do it. Another thing to do with these is for linearity. You can put a relay that actually sits on the stem and watches the movement, and then it can actually not only rearrange it, but it can actually keep it, making sure this more linear on the actuator. And these are programming devices, and you can see these are all the different kinds of relays. You get not all of them, but pretty much all of them. 1-to-1 ratio, ratio relays, direct acting, reverse acting, averaging relays, ratio high selective 2 inputs, low selective 2 inputs. In other words, if you're trying to figure out what's happening in VAV boxes, and you bring the signal, the output signal, into a selector, and it'll tell you, it'll send the lowest of 2 or the highest of 2, or they go clear to 6. That's 6, right? They go 6, and they also have 10. So you can input a whole bunch of devices, and this is the way we were doing logic. Like if we were trying to analyze a VAV box system, we want to know how many of them are closed or open. We could tell by watching that slow. But it's really cumbersome. It takes a whole bunch of installation to do it. It's not like today in electronics, we just change a program. This was required. And then we have 3-way solenoid valves. We have manual potentiometer, so we can actually make a set point adjusted manually. So there's all kinds of devices to change the logic. But like I said, that you go down a rabbit hole really quickly with that. And that's a brief pneumatic. It wasn't very long, but it gives you the basis of pneumatics. And we still use those. And if you want to use them for explosion proof, you just get sensors and you run air to the system and it operates. And then you can always convert all the signals to electronics outside the space if you need that. So pneumatics are possible to still use, mainly for doing actuators one way or the other. So I hope this was helpful. I know that we don't use a lot of pneumatics, but at least it gives you some education of what they are. Thanks a lot for watching. I really appreciate you. Have a great day, and I'll catch you on the next one. Thanks.